So we now are in the realm of metric spaces. So for whatever reason, I decided to call K my set, D sub K is the metric, not X anymore. Tau for me is going to be the topology given by this metric, right? Remember, the topology given by a metric is a topology where the open sets are precisely the open sets according to that metric. And let's recall the definition, the topological definition of compactness, meaning that any collection of open sets that covers K has a finite subcollection that also covers K. What we're going to do over the next few videos is to prove a series of equivalences of this definition. They're not true for all metric spaces. They don't even make sense, perhaps, for all metric spaces. But for metric spaces, all these things turn out to be the same. So first one is K is compact, so that's that. Second one is that any continuous function defined over K achieves the inf and achieves the sup. So we saw that K compact implies this for general topological spaces. The other direction is not necessarily true for all topological spaces. You need some extra assumptions, but for metric spaces, one and two are equivalent. 3 is actually a consequence of 2, that any continuous function from X to R has to be bounded. And that's just saying, okay, if the infimum and the supremum are achieved, the infimum cannot be minus infinity, right? Because it's just the value of the function at some point. And the supremum cannot be plus infinity, because the supremum is just a value of the function at a point. So therefore, the values of f are between two real numbers. They're bounded. So 2 clearly implies 3. Well, let me draw some arrows here. We're going to be seeing soon that 3 implies a seemingly much different property, which is, okay, let me say, these are done. This is something that we're going to prove later. That if any continuous function from X to R is bounded, or every continuous function from X to R is bounded, then the metric space K has to be complete, because these sequences have to converge. It also has to be totally bounded. And totally bounded means something very specific, that for any radius epsilon that I give you, you can find me a collection of open balls of radius, or closed balls of radius epsilon that covers the entire space K. So totally bounded is something like this, except that instead of taking collections of open sets, I take collections of closed balls, or open balls would be the same. But it's just saying that for any epsilon, I have a finite number of closed balls of radius epsilon that cover the entire space K. We'll get to that in a later video. Okay, so 3 implies 4 is already going to be less trivial, less immediate than the other things. So 4 implies 5 is also going to be quite non-trivial. And we're going to show that if K is complete and totally bounded, then every sequence in K has a subsequence that converges to a point of K. So a metric space with this property is sometimes said to be subsequentially compact, meaning, or sequentially compact. It doesn't matter which one you use. It just means that, okay, it's this property that we used to from the real line that every sequence in a compact set has a convergent subsequence that converges to a point in that set. So that's what we have over here. So we'll see that 4 implies 5. And we'll also prove in a couple of minutes that if a space is subsequentially compact, then all continuous functions must achieve the inf and the sup. So in that sense, we'll see that 2 implies 3, implies 4, implies 5, implies 2. Therefore, all from 2 to 5 are equivalent. We're still missing something, right? So eventually I have to prove that all of these properties together imply 1. And in fact, what we're going to do is to show that if I have a metric space where all continuous functions achieve the inf, and this metric space is also totally bounded, then it has to be compact according to the topological definition. So this grand equivalence theorem, it's, as I said a few times already, involves some non-trivial steps, and we're going to be doing it little by little over a series of videos. Right now, I want to emphasize that I already know that 1 implies 2. we already know that 2 implies 3 by this argument I gave, that if the infima and the suprema are achieved, they're both finite, therefore f takes values between two finite real numbers. And I want to argue too that 5 implies 2, and that's a classical argument that we have in the real line as well. And once we, and then we're gonna start to see 3 implies 4. We're gonna show that any metric space where continuous functions are bounded has to be complete, right? That's sort of non-trivial, but we'll see why that is. It's non-trivial, but it's not hard either, because some of the work for this has already been done as exercises earlier in the class. Okay, so you'll forgive me for my bad Blackboard technique as usual. I'm just gonna say, okay, how does 5 imply 2, right? So how does okay, so let me I need better weapons to erase the Blackboard right now. Right, so as I erase the Blackboard, I'm going to try to remind you of what we do with the real line. Suppose that every sequence has a convergent subsequence. Now take a continuous function and take a sequence of points in the space K whose values of f approach the infimum. Now what you have to do to finish the proof is take a convergent subsequence of that sequence and show that the limit of that subsequence achieves the infimum. And the same thing for the supremum, right? So I'm just gonna do one of these things. So if k dk is subsequentially compact, meaning every sequence has a convergent subsequence that converges element of k, then for all f from x to r continuous, there exists an x star in x such that f of x star is equal to the infimum of f of x. So this might look funny because in the previous video we proved that if a topological space is compact, then we have this. But of course, at this point we don't know that subsequentially compact and topologically compact are the same thing for metric spaces, right? So I cannot simply say, well, we proved this before. No, this is going to be part of this long proof of the equivalence of subsequential compactness with boundedness of continuous functions with topological compactness, and etc. Okay, how do we prove this? Again, well, let me call M minus just infimum. And I'm allowing here for a potentially unbounded function that has infimum equal to minus infinity. But that doesn't really matter because we know that there exists a sequence in the real line such that m sub n is greater than m minus for all n, and m sub n converges to m minus, right? That's easy. Just take a decreasing sequence, go to m minus. Well, if m minus is just a real number, then I can take m sub n to be n minus plus 1 over n, say. Otherwise, I can just take some sequence that goes to minus infinity, and then we're done. Now we're going to use the property of the infimum. Since m sub n is greater than the infimum, which is m minus, which is inf f of x, for all n, there must exist a point x sub n in the space x, which has a value of function, well, that's f of xn is less than or equal to, well, actually less than m sub n. Let's say less than or equal because it doesn't matter. And of course, this value also has to be greater than or equal to the infimum, right? The infimum is a lower bound. So all function values over x, all values of f over x are lower bounded by the infimum. Okay, now comes the time, and this is really the same argument that we used over the real line. Now comes the time to use subsequential compactness, which means that there is a subsequence of these guys that converges to, sorry, I call this x, not x, right? It's k, sorry. And there's so many x's here. Yeah, sorry about that. So I can take a subsequence that converges to x and k. I also know, well, mn sub k, so I take the corresponding sequence of these values, and this has to converge to m minus. Why is that? Well, I have a convergent sequence of real numbers. Now I'm taking a subsequence. That subsequence must have the same limit as the original sequence. That's a theorem about analysis over the real line, as usual. Now, these two things together, they tell me that m minus, okay, so f is continuous, right? So if since f is continuous, I know that the limit of f of x sub n sub k is equal to f of, sorry, let me call this x star, just to match the guy on top. Right? So, and why is this greater than this? Well, for any k, f of x sub n sub k is greater than m minus. Now, this is also less or equal to the limit in k of m sub n sub k, which is just m minus. So it's yet again one of those sandwiching arguments, right? So I just showed that f of x star, which is the limit of f of x sub n sub k, is between m minus and m minus. So it must be equal to m minus. And it's at this point of the proof, notice this is non-trivial, right? So it's at this point of the proof that we show that m minus cannot be minus infinity, right? So because, well, this limit could be minus infinity in principle. However, I just showed that this limit is equal to the value of the function at some point. And this function has real values, so there's no way this number can be minus infinity. Still, I know that f of x star must be equal to a minus, which is infimum, and now I'm done. So I've proven that when a space is subsequentially compact, the infimum is achieved, and this is the argument, the same classical argument that we use over the real line, over RD, it's just the same thing. Okay, so that is 5 implies 2 in the big theorem, the great equivalence, as I called it, the grand equivalence, sorry. But there's a lot missing, and I want to get started with that. So remember there's this item where I say that if you have a metric space where all continuous functions are bounded, then it must be that this metric space is complete. And this is going to use an exercise that we did before. So we're going to prove that in counterpositive form. By arguing that if I'm going to argue that if a metric space is not complete, sorry, I need to erase some more. If the metric space is not complete, then there is a continuous function defined over that space that's not bounded. Okay, prob. Okay, let me actually use X here. Sorry, I need to erase some more. So again, what I'm going to show is that if a metric space is not complete, then there's a continuous function for the space that's unbounded. Okay. Right, so I'm bounded above if you want, but the above and below don't really make too much of a difference in any argument involving continuity. So how do you find this function? So I'm going to draw the picture, and then I'm going to explain which exercise this picture relates to. What does it mean for a metric space to be non-complete? It means basically that it has a hole. So here I have X, and this is all intuition, right? So there's a hole somewhere, so there is a point that should be in this space. I'm going to call this point, I don't know, alpha. There's a point that should be in the space, but it's not. So this is not a point in the space. This is a hole. It's like think of X as the real line minus 0 and alpha 0, right? It's a point that's missing there. What does it mean that a point is missing? It means that it cannot get arbitrarily close to this point, but not actually reach the point. So the function I'd like to define, if I define a function like this, right? So this is still intuition. Distance from X to alpha. Alpha is fixed. So we know this is a one Lipschitz function. It's positive because no point in X is equal to alpha, right? Alpha is a whole. And, but in fact, the infimum of g of X for X and X is 0 because you can get arbitrarily close to alpha. Well, this is not an unbounded function, right? But then if I have these things here, then f of x being equal to 1 over g of x is continuous. It's actually non-negative. And the supremum is plus infinity. Why? Because g gets smaller and smaller as you approach alpha. And therefore f gets larger and larger. Okay, how do we turn this into a rigorous argument, right? Okay, there are two ways. One of them is very roundabout, is to define the completion of a metric space. And then we can say X is contained in the larger metric space that's complete. And therefore, there really is a hole in X. There are points in the completion, there are not in X. But let's do something different. So the hole here is going to be replaced by a Cauchy sequence, right? So I still have the hole in the drawing. So I have a Cauchy non-convergent sequence, right? So what does it mean to have a non-complete metric space? It means that there exists at least one Cauchy sequence that's not convergent. And now I'm going to define G without the scare quotes. I'm just going to define it as the limit as n goes to infinity of distance from x to x sub n. And here's the exercise that we did. We proved that such a function is well defined, that this limit exists for all x. That comes from the Cauchy property of x sub n. This limit is actually a Cauchy function. No, sorry, not a Cauchy function. It's a one Lipschitz function. It's positive because if this limit is 0 for x, it means that x is the limit of the sequence x sub n, but the sequence x sub n has no limit. So this function is always positive. It cannot be 0, right? So the metric, these values are all non-negative, and they cannot be 0. The limit cannot be 0. Okay, but this function, in spite of being positive, it's sup and continuous, its infimum is equal to 0. Why? Because if you evaluate this function along the points of the sequence, x1, x2, x3, x4, etc., you can prove using the Cauchy property that g of x sub n goes to 0. So that's in the exercise we did before. If you didn't do it, now is the time to do so. So we have this Lipschitz function that's positive but has infimum 0 equal to 0 over any non-complete metric space. And that solves the problem as before, right? So if g is never 0, 1 over g, which I define as f, is a continuous function that's positive, and its supremum is infinity because g gets smaller and smaller, f gets larger and larger. And then we're done. So at the very least, we proved part of an implication that we have. What we said is that if all continuous functions from x to r are bounded, then your metric space has to be complete. Here we proved it in counterpositive form. If x is not complete, there exists at least one continuous function over x with values in r whose supremum is plus infinity. The function is not bounded. And with this, we finish this video. Thank you.